We're talking about generators for a group. So G is a group, S is some non-empty subset of the group, then angle bracket S denotes the subgroup of G generated by S. One way to define it is to take the intersection of all the subgroups of G that contain S. And you can verify that S is really, this angle bracket S is really the smallest subgroup of G that contain S. And if you have a subgroup of G, you say that S is a set of generators for that subgroup if S generates H, meaning angle bracket S happens to be H. Concretely speaking, this subgroup angle bracket S contains all products of powers of elements of S. All expressions of the form a1 to the i1 dot 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 an to the in product, where a1, a2, an came from S and i1, i2, in are integers. And another way to write would be just using plus or minus powers, where gives you exactly the same thing, because if you have some positive power of an element, you can write it a times a times a times a times a 5 times. And if you have negative power, you can write it using inverses. Yeah. So taking all such expressions and all the expressions on the left gives you exactly the same set. Okay. We saw some examples, like if you take a subgroup of Z and assume that it contains 6 and 11. If it contains 6, so H is a subgroup of Z and 6 and 11 belongs to H. If you know that, then you also know that 2 times 6 is in H. You also know that 2 times 6 you also know that minus 11 is in H, because 11 is in there. And you know this is also in H, but that's 1. And once you know 1 is in H, you know that all multiples of 1 is in H. So all the numbers are in H, so H is Z. So we say that 6 and 11 generate Z. The smallest subgroup of Z that contains 6 and 11 is equal to Z. But if you do the same exercise with 4 and 6, you find that you only get the multiples of 2. You only get the multiples of the GCD. So we say that 4 and 6 does not generate Z, rather they generate 2Z, right here. Of course, 2 is also a generator for 2Z. So this subgroup 2Z is actually cyclic. It can be generated by just a single element. And if you think about it a little bit, you soon arrive at the theorem that the subgroups of Z are exactly the following. Well, you always have just the 0 subgroup and the whole group Z. That's a subgroup. But then you also have 2 times Z, which are the even numbers, 3 times Z, which are the multiples of 3, which is a subgroup generated by 3, 4Z, etc. And in fact, you can say Z is 1 times Z, and 0 is 0 times Z. So in particular, all these are cyclic. And a very quick sketch of why, well, let H be a non-zero subgroup of Z, meaning there is some A in H that is non-zero. Then A and minus A both are in H, and at least one of them is strictly positive. So H contains a positive number, meaning a natural number. So take, n to be the smallest natural number in H. And then you can show that H is basically just all multiples of n. So that's how you find a generator. You just take the smallest natural number in H. And the reason is, if you take anything in H, you can do division with remainder, You can write it as some multiple of n plus a remainder where this is between 0 and n, but strictly less than n. But now this r is a minus a multiple of n, and this is still in H. So this cannot be non-zero, because if it was non-zero, then it would be a smaller thing than n and in H. But n was the smallest thing, smallest natural number in H. So r has to be 0, so a has to be a multiple of n. So I won't write the rest. I'll let you fill this in. In fact, there is a more general theorem that says that every subgroup of a cyclic group is cyclic. And in fact, this would even follow quite quickly once we have a little more theory, so I won't bother right now proving it. But maybe we can illustrate it with an example. We illustrated with Z already. Let's figure out the subgroups of 6Z, Z mod 6Z, a finite cyclic group. The Z mod 6, which is, it has only 6 things, so this is a fairly easy group. And here again, by 4 I mean 4, the image of 4 in Z mod 6. Okay. So that's my G. The operation is plus, the identity is 0. Of course, you have the 0 subgroup, and you have G itself. Now let's say a subgroup contains 1. If it contains 1, then it contains 1, 2, 3, 4, 5, 0, everything. So it's the whole group. Similarly, if a subgroup contains 5, 5 is really minus 1. So if it contains 5, then it contains 1. So it contains everything. Tells you that if a subgroup contains 1 or 5, then it has to be the whole thing. So if you have a proper subgroup that cannot contain 1, cannot contain 5, so you're only left with 2, 3, 4. If you start, say a subgroup contains 2, then it contains 2 plus 2, which is 4, and then 2 plus 2 plus 2, which is 0, and you can check that this forms a subgroup. That's the subgroup generated by 2. Similarly, if you start with 3, and 3 plus 3 is already 0, you can check that this is a subgroup. And if you take the subgroup generated by 4, well, it will be the same as this one. And if you take 2 and 3, or 3 and 4, as soon as you take 2 and 3, you get 1, so you get everything. So that is a quick argument that shows that you already see all the subgroups here. There are 4 subgroups. And here is the sort of a picture that remembers which one is contained in which. The arrows tell you which is contained in which. So there are 4 subgroups, G itself, just 0, and then this one and that one. You can do the similar exercise with maybe Z mod 12, Z mod 15 to get a sense of what is going on. If you want to move beyond cyclic groups, maybe I'll do a couple more examples. Let's look at G equals Z2. So that group we can actually picture. It's the points on the square grid in the plane, etc. So here is 1, 0, here is 0, 1, here is 1, 1, etc. So really, that is the set, the operation is vector addition, and the identity is 0, 0. So you can check rather easily G is generated by the standard basis vectors 1, 0 and 0, 1. If we call it E1 and E2. Because if you take any element of G, like minus 3, 5, you can write it 3 times, minus 3 times E1 plus 5 times E2. Well, that doesn't look like this sort of expression on the left. If you look, we said that the group generated by a bunch of things looks like this. But if you remember that we are talking about additive notation here. So this expression corresponds to the multiplicative notation of E1 to the minus 3 times E2 to the 5. In the multiplicative notation, we would have written it like this. But now, instead of dot, we have a plus. So instead of the power, we have multiple. Okay. So every element of the group can be written in terms of E1 and E2 in this way. So G is generated by E1 and E2. You can write down other generators, like, I don't know, these two would do, you can check. Once you get these two, you can subtract them and get 1, 0. Once you get 1, 0 and 1, 1, you also get 0, 1. But once you get 1, 0 and 0, 1, you get everything else. It doesn't have to be just two vectors, by the way. If you add a third one, they still generate. I don't need the third one, so what? I can still get every element of G in terms of these three. Okay. On the other hand, if you just take one vector, like, I don't know, 1, 1, then G is certainly not that. If you just take 1, 1 and generate a subgroup using it, what do you get? You only get the points on this line. So that is what a proper subgroup looks like. Or say if you take even 1, 1 and 2, 0. I claim that they don't generate either. If you play around a little bit, you'll discover that if you start with these two vectors, where are they? Here is 2, 0, here is 1, 1. You only get every alternate vector in this sense, the ones that I'm circling. You don't get the other ones. It's sort of the checkerboard configuration. Okay. A little more. You'll see what I mean. So that's what a proper subgroup looks like. So this is a good way of constructing lots of subgroups of a group. You take a bunch of elements and see what they generate. Lastly, we talked about this permutation group. If you take the simplest permutations, 1, 2, 2, 3, 3, 4, 1, 2 means the permutation that switches 1 and 2 and fixes everything else. 2, 3 means it's the permutation that takes 2 to 3, 3 to 2 and fixes everything else, etc. I claim this requires some argument that S4 is actually generated by sigma 1, sigma 2, sigma 3. S4 means all permutations of 1, 2, 3, 4. For example, if you take the permutation that takes 1 to 2, 2 to 3, 3 to 1, and fixes 4, you can write that, I think, something like this. Let's check. So that would be sigma 1, sigma 2. Let's take 1 and apply sigma 2 first. Remember, we apply this one first and then that one. That's how the composition works in this group. Take 1, apply sigma 2, which means flipping 2, 3, so 1 stays at 1. Then apply sigma 1, goes to 2. And then take 2, goes to 3, stays at 3. And then 3, apply sigma 2, goes to 2, and then apply sigma 1. That's flipping 1 and 2, so goes to 1. So indeed, 1 goes to 2, 2 goes to 3, 3 goes to 1. Similarly, you can write everything, you can check. More generally, let sigma 1, sigma 2, sigma n minus 1 be the elements be defined by 1, 2, 2, 3. This is the one that flips the last two numbers. Then this is a particularly nice set of generators for Sn. Maybe when we play with Sn some more, we'll talk about this more. Maybe one remark. This is not the cycle notation for this permutation. The cycle notation is 1, 2, 3. You see, these cycles are not disjoint. It's simply saying that this permutation here is product of sigma 1 and sigma 2. Okay. So that's, I think, enough example for generators and relation. Generators for a group. We'll move on to homomorphisms and isomorphisms next.